Hello, everybody, and welcome to week 7 of Math 4400. This week we're going to talk about basically some complements to what we did last week. So last week we talked about cryptography, and today in particular we're going to talk about primitive roots a little bit more and discrete logarithm a little bit more. So just to give some context for where we're at. So last week we talked about cryptography. We talked about two different schemes for doing cryptography. So one was Diffie-Hellman. This was the scheme where you did some modular arithmetic to exchange a shared secret, and then you could use that to transmit messages from one person to another using, for example, a shift cipher. Okay, and then the other one was RSA public key encryption. That's the one where one person multiplies together two big primes, does some computations, posts some data publicly, and then people are able to send them encrypted messages. Okay, so we sort of studied these two schemes and how they work. And I just wanted to comment on two important things. So there were some key ideas that were used in both of these. In Diffie-Hellman, in particular, we used the notion of a primitive root. So this is what we're going to talk about more today. But then also in both of these schemes, we really used even though we didn't use very big prime numbers in our own computations just to keep it manageable, like if you actually want to use these in practice, you have to use big prime numbers. So this is sort of an idea. We haven't really talked about big prime numbers yet, but there are really big prime numbers and you sort of have to use these. So we're going to talk a little bit this week about big prime numbers as well. Okay, and I just want to recall that the reason these cryptography schemes worked was because certain problems are difficult. So for RSA, the problem that's difficult is factoring numbers. So if you don't, like it's easy to sort of produce a product of two big prime numbers, but if you just sort of showed someone that product without telling them how it factors, it's hard for them to find the factorization. So it's hard for them to find those two primes, and that's why RSA works. And then Diffie-Hellman sort of depends on the difficulty of discrete logarithm, which means sort of if you have a primitive root and you raise it to some power, even though if you know what the primitive root was, it's difficult to tell what that power is. So okay, but we'll come back to that in a second. So today we're going to focus on primitive roots and discrete logarithm. And then on Thursday, we're going to talk a little bit about big primes. Okay, so let me recall the definition we used last week of a primitive root. So this applies for any finite field F. The thing to have in your head is, of course, Z mod PZ or FP. So a primitive root in F is an element G in F cross, so a non-zero element, an element with multiplicative inverse, such that every other element of F cross can be written as a power of G. In fact, you could do a little bit better. So last week I just said can be written as a power of G, but here I'm sort of being specific that I only have to go up. So I start at G, so 1 is sort of G to the 0. And then I only have to go up to the number of elements in F cross minus 1. So this is the biggest power I have to go up to. Okay, so that's what it means to be a primitive root. And last week on the homework, for example, you computed that 2 is a primitive root in F13, 3 is a primitive root in F31, 5 is a primitive root in F47, 6 is a primitive root in F41. You also did a computed primitive root in some other fields, like where you constructed using polynomials or using the Gaussian integers. And so we saw, at least in lots of examples, primitive roots exist. And implicit in the description of the Diffie-Hellman algorithm is the statement that primitive roots always exist. And so today I want to say just a little bit about how you justify that claim that there always is a primitive root. Okay, so before doing that, I just want to sort of reformulate one notion. This is related to something we've talked about before. But if I have a group G, so remember a group is just a place where you can, you have a single operation. So in this case, the main group we'll be looking at will be F cross. So the group of elements of the group of non-zero elements in the finite field F. And that's a group under multiplication. Okay, so in any group though, we're going to say the order of an element little g is the smallest positive integer k, such that when I take g and I sort of multiply it together k times, which we write is just g to the k, I get the identity element e. Okay, and so we're gonna, when we talk about the order of a group element, we're gonna write ord of g. If you look in the textbook, I sometimes just writes O of G, but we're going to write ord of G to keep things completely clear. And this number has actually come up already when we talked about Lagrange's theorem. So when we stated Lagrange's theorem earlier, what we said is that if you have a group and you have an element, little g in that group, then if you raise it to the size of the group, which we write sort of bars g. So if you take g to the, so previously we stated Lagrange's theorem as saying that g to the size of g is the identity element. So last time we stated Lagrange's theorem, that's what we said. But if using this notion of order, we can be a little bit more precise. And we can say, actually, what's really true is that the order of any element divides the size of g. So that pretty easily implies that g to the g is equal to e, because sort of g, I write g is equal to q times order of g, then g to the g is equal to g to the ord g to the q, which is e to the q, which is e. So g to its order is equal to the identity element. That's sort of by definition, because the order is what's the smallest positive integer that's such that this holds, but in particular, this holds for the order. So this is the identity element, and then if I raise the identity element to any power, I just get the identity element back again. Okay, but this statement is sort of slightly more precise. So it's not just that if I raise an element to the order of the group, I get the identity element. It's really that the order of that element is a divisor of the order of the group. So the smallest integer, such as is true, divides the order, the size of the group G. And if you go back and look at how we proved Lagrange's theorem, so this was done in one of the video lectures. If you look at this proof, you'll see that really, in the same proof we wrote down then, implies a stronger statement. We just hadn't sort of defined this notion of the order of an element yet at that point. And somehow, when we used it last time, we used it for this application of like computing like the last 5 digits of a number. And in that case, we only really needed sort of this statement. But what we're going to do here, we want sort of this finer statement. Okay, good. So how is this connected to primitive roots? Well, let's make some room. So, well, actually, sorry, let me write this down in a second. Okay, so I'll say in a second how this is connected to primitive roots, but first let me just write down an example. So if I look at G to be the group F11 cross, so that's just all the non-zero elements in F11 where the group operation is multiplication, then the size of that is 10, because I start with 11 things in F11, and I throw out 0. So I have 10 elements in there. Let me just write down what all those elements are. They're 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then what's the order? Well, the order of 1 is just 1, because 1 is the identity element. So 1 to the 1 is equal to 1. Good. And if you run through all the powers of 2, you'll see the order of 2 is 10. You do for 3, 4, 5, you'll get sort of the order is 5. Then 6, 7, 8, you'll get the order is 10. And then 9, you'll get the order is 5 again. And if you do a 10, you'll get the order is 2. This is because 10 is sort of congruent to -1 mod 11. So if I do -1 squared, I get 1. Okay. Okay, good. So that's an example. And well, this line, whoops, we've seen before that 2 is a primitive root mod 11, and this entry is sort of equivalent to that statement. So this is what I was about to say earlier. So saying that 2 is a primitive root in F11 is the same as saying it has order 10, because 10 is 11 minus 1. So let me sort of make the general statement in this theorem. So if F is a finite field with n elements, so here n was 11, then, well, first part of this statement is just that G and some element G, like 2, is going to be a primitive root if and only if the order of G is n minus 1, which is also equivalent to saying that G to the D is not 1 for all proper divisors of n minus 1. So this looks like the criterion you guys used on the homework for last week, and I'll justify it now in a minute. But then the other part of the statement is the thing that says there exist primitive roots. So it says a little bit more than that there exist primitive roots. It says there are actually, it says exactly how many different choices there are of primitive roots. So there's going to be phi of n minus 1 primitive roots inside of F. Okay, so in this example above, let me fill this in now. I said 2 is a primitive root, and then also 6, 7, and 8 are primitive roots in F11. That's because they have order 10. As I wrote. Yes, good. They have order 10, which is n minus 1. So good. So n minus 1, so n is 11. N minus 1 is 10, so these have order 10. And nothing else has order 10. So there are 4 primitive roots. On the other hand, so let me now look at this second part. If I compute phi of n minus 1, well, that's phi of 11 minus 1, so this is phi of 10, which is phi of 5 times phi of 2, which is just 4 times 1, which is 4. Okay, so that at least checks out in this example. Here, phi of 10 is really equal to the number of roots I saw, a number of primitive roots I saw in this example. Okay, so how do we prove this theorem? Well, let's talk about the first part. And so again, this first part is basically the condition we were using on the worksheet. So that's so it was this condition that let us check whether something was a primitive root without having to sort of just compute all the powers and see whether we got everything. Okay, and so the idea is, well, if I have some element whose order is n minus 1, then if I write out the elements e, g, g squared, g cubed, all the way up to g to the n minus 2, these are going to be distinct. So this isn't quite immediate, but it uses the same argument we used when we proved Lagrange's theorem. So if 2 of these were equal, you could sort of take 1 times the inverse of the other, and you'd get some smaller power of g that was equal to the identity element. But the order is supposed to be the smallest power of g that gives you the identity element. So these really have to be distinct. Okay, but that's n minus 1 things. Sorry, because I started at g to the 0 and went up to n minus 2. And well, in F cross, there are only n minus 1 things. So somehow if I have n minus 1 distinct things, and they sort of live inside some other n minus 1 things, I really have to hit all of them. So this justifies that if the order is equal to n minus 1, then really I hit everything as a power of g. Okay, and then, well, to see that the statement that the order of g is n minus 1 is the same as saying that g to the d is not equal to 1 for all proper divisors of n minus 1, this really just is Lagrange's theorem. So we know the order of g always divides n minus 1 by Lagrange. So if you want to see that it's equal to n minus 1, you just have to check that the order isn't any smaller. But since it divides n minus 1, the order has to be some divisor. But g to its order is equal to 1. So as long as g to the d is not equal to 1 for any proper divisor, really g has to have order n minus 1. So the second part is sort of really just using Lagrange's. So this if and only if the order of g is equal to n minus 1, if and only if g to the d is not 1 for all proper divisors. This is just really coming from the Grange's theorem. Okay, so that's part 1, and this is, again, just justifying this fact we were using to check whether something was a primitive root on the homework last week. The more interesting part is this thing that says there really exist primitive roots and sort of exactly how many there are. Okay, and we're not going to prove that all the way. I just want to say sort of what the key idea is. So, I mean, somehow the issue that could sort of stop this from happening is like maybe like n is 15, or sorry, let's say like n is, yes, let me do a better example. Let me say like n is 9, and then sort of phi of n, so then n minus 1 is 8. And so if you're looking sort of for elements that have order 8, but maybe it turns out like everything has order 4. But if sort of everything had order 4, like then you'd have so like 8 things that had order 4. And that would be too many things with order 4, because sort of anything with order 4 is a root of the polynomial x to the 4 minus 1. And this can have sort of at most four roots. And this is sort of the general idea of what you have to show. You have to show that you can't have too many sort of things of smaller order. And if you sort of show that there aren't too many things of smaller order, that means you must have things of order n minus 1. And then if you sort of do that carefully, you actually get this precise count. There are phi of n minus 1 things with roots with order n minus 1. Okay, so again, so the main idea is that if this equation g to the d is equal to 1, is the same as saying g is a root of x to the d minus 1 in F, and we know there are at most d roots. Okay, so turning that into a proof is a little bit more complicated than I have time to do in a 30-minute lecture. But if you're interested in sort of reading out the proof, reading out how you sort of turn this into a careful proof, you can look at proposition 20 in the textbook, which is on page 73. There's one fact we haven't talked about that will get used in that proof, which is that the sum of all of the divisors, so I take some n and I take the sum over all the divisors of n of phi of d, then I get n back. So this comes up in the proof. And so this is discussed on the worksheet for this week as exercise 4. And it actually came up in a sort of specific example on an earlier worksheet as well. Okay, so that's this main theorem about primitive roots. Again, just the first part tells you how to check whether something's a primitive root using its order. And this is something we used in the worksheet last week. And then the second part is a statement that guarantees that there always is going to be a primitive root and tells you exactly how many there are. Okay, so the other thing I want to talk about today is discrete logarithm. And so this came up when we were doing Diffie-Hellman, and I just want to make the notion a little bit more precise than we did last week. So let me take a finite field f, and let me just write the size of f as little n, just so I don't have to keep on writing size of f. Okay, so then I'm going to take g to be a primitive root in f of f. So it's one of those elements guaranteed to exist by that previous theorem. And then I'm going to look at the map, which goes from z mod n minus 1z, so n minus 1 is the order of g, to f cross, and it just sends a number k to g to the k. So some of the reason this only depends on k modulo n minus 1 is because n minus 1 is the order of g. So this gives me a map, k goes to g to the k, and the definition of a primitive root says that this is a bijection. So a one-to-one map. So just to recall, a bijection means sort of if I have something over here, there's exactly one way to hit it from starting from something over here. Okay, but again, that's just a rephrasing of the definition of a primitive root, which said exactly that I could hit everything in exactly one way. There I am. Okay, so whenever I have a bijection, I get an inverse map. So an inverse map just sort of takes some element x in f cross, and it sends it to I of x. So I'm going to call this map I. It sends it to I of x, which is defined to be the unique element such that g to the I of x is equal to x. So this is just what it means to be the inverse map to this map up here. And inverse maps always exist when you have a bijection. Okay. And so this I of x, this inverse map, we call the discrete logarithm for f with base little g. And the reason it's called the discrete logarithm is, well, because logarithm traditionally is something about the real numbers. The real numbers are not discrete. So the real numbers are like continuous. There's a continuum of real numbers. But sort of f cross, like this finite field, this is something that's discrete. It's just sort of a finite set of points, you can think of it. A finite set of numbers. So there's no sort of continuumness to f cross. So that's the discrete part. And then logarithm is because otherwise it behaves just like the logarithm does for the real numbers. So in particular, it takes multiplication and turns it into addition. And as a special case that it takes sort of raising to powers and turns that into multiplication. And it sends 1 to 0. So these are easy to check just from the properties of raising to a power. So somehow these are the opposite properties of what raising to a power does. So raising to a power sort of turns addition into multiplication and sends 0 to 1 because g to the 0 is 1. Okay, good. These are the properties that the logarithm satisfies, and these properties are some of the main reasons the logarithm is a useful tool. So the logarithm serves something that takes a positive real number and sort of multiplication on the positive real numbers and turns it into a just real number and then turns sort of multiplication into addition. So a logarithm is the inverse map of the exponential function, where by the exponential function, I just mean the exponential of t is e to the t. Okay, and then we have, so here when I say log without any base, I mean log base e. And yeah, we have log of xy is log of x plus log of y. Log of x to the k is k log x. And log of 1 is equal to 0. So these are the standard properties of the logarithm for real numbers. They look just like the properties up here for the discrete logarithm. And somehow what's most useful about logarithm is that you can use it to solve equations. So like somehow equations that involve multiplication are harder to think of or write down solutions to than equations that involve addition. So when you see equations that involve multiplication, like for the real numbers, a good way to handle them is to apply the logarithm to turn them into equations that sort of involve addition. And so we use discrete logarithm the same way. We use it to sort of turn equations, we use it to try and solve equations involving multiplication in finite fields by replacing them with equations just involving addition. Okay. Good, so we'll see some of that on the worksheet. And then I just wanted to sort of point out the connection before finishing with last time. I mean, computing this inverse map is the thing that breaks Diffie-Hellman. So Diffie-Hellman, when you establish your shared secret, you'd take some primitive root and you'd send out g to the a. Like you'd pick your number a and you'd send out g to the a. Your partner would send you g to the b. You'd both raise these to powers and you'd get a shared secret. And you're sending out g to some power, and anyone intercepting, like anyone listening, knows what g is, and they'll see this number you sent out, which is g to some power. So if they can compute the inverse logarithm with base g, then they can sort of find your secret number a, and using that they can crack your they can sort of also find your shared secret. So somehow computing the inverse logarithm, so computing the discrete logarithm, which is this inverse map, is exactly how you would break Diffie-Hellman. So The reason Diffie-Hellman is still a secure thing to use is because it's very difficult to compute this inverse map. Some of the only way to do it really is just to write out all of the powers of G. And that's not very efficient when you're working in a very large finite field. So it's not like it's not like the real numbers where you don't need to sort of compute logarithm of everything or exponential of everything to sort of compute log of one thing. Like over the real numbers, you have just a power series formula for logarithms. So somehow you know how to compute one logarithm without computing all of them. But that's not true in finite fields. I mean, in finite fields, like there's like the only way to compute one logarithm is sort of compute all powers. Okay, and that's what makes it hard. Okay, but great. I will see you in class on Tuesday.